Hello, hello. Excuse me. Hello, Josephine. Good to see you. Hello. We go start. Good afternoon. Okay, good. Hello, Maria. Good to see you. Good afternoon, Alexis. Good afternoon, Katie. Good afternoon, Eric. Good afternoon, Emily. Good afternoon, Stephanie. Hi, Victoria. Good afternoon, Maria, in person and in text. Good afternoon, Logan. Good afternoon, Paulina. And hello, Josephine. It is good to see you. I think I said that, but okay. All right. Oh, and I said Paulina. And Jada, nice avatar, and Alexis. All right, awesome. Hold on. The board is joining. We're trying to join. Okay. Oh, and more people in the waiting room. Sorry, here it comes. Okay. Okay. Oh, wait, can you hear me actually? Wait a minute. I'm sorry. You can. Okay, thank you. So I can't hear you. That's the thing.
Sorry,
Hold on,
I'm late.
sorry.
I just got out of a meeting.
Thank you. Sorry. What? Oh, hello, Claudia.
I just got out of a meeting. I'm sorry, I'm late.
Oh, no, that's fine. No, we're just start. Okay, no, thank you. What are we doing? Okay, people are rejoining. Okay, no, thank you. And I'm the board is just coming in also. Okay, and I thought people couldn't hear me anyway. Okay, here we go. Okay. 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 So we are going to and good afternoon, Shirley, and good afternoon, Jenna. Good afternoon, Shy. Thank you for saying so. And yes. Okay. Oh, sorry, this is in direct chat, but absolutely good afternoon, Claudia. Awesome. Okay, there's a question in the direct chat about the very last question of the big old duck homework, which I assume means the big old duck question, which is absolutely. I hope it means that. Someone's asking me direct chat. Are we going over the last problem in the big old duck homework? And if by the last problem you mean the problem called big old duck, yes, that is exactly the plan for today. I mean, I hope that's what you mean, because that is it. Yes, awesome. Okay, that is exactly my plan for today. And in fact, my plan is to get to it with less preliminaries than there are sometimes. So yes, so the plan today is literally that, is the big old duck problem, which is a cool. Thank you, other direct chat person. Got you. Thank you. The big old duck problem is a big problem. I actually believe we're getting to the point sometime where I believe some of you might have looked at old videos or gotten help from old class materials on it, which is great. But I'm just suspecting that is the case. And with homework, that's awesome. I mean, you might want to tell me that that's what you did, whatever. So I know that actually a fair number of people in the class did get some solution to that, or maybe even a correct solution. But I think with help, and that's great. So so what I'm saying is absolutely that problem is worth talking about. It is a big leap forward. It's very related. It's a transition to the next homework. It is also very related to your lab 4, which you did somewhat recently. I'll make those connections when we start talking about it. It's not an easy problem. I think it's worth seeing for everybody, even if you happen to have gotten it right. It's definitely a thick problem. I mean, doable, fair, legitimate. And the other thing is, often, as you may have noticed, maybe when we have a midterm exam in this class, which we are going to, which there's now been announcements about in Google Classroom, usually one of the big problems on the midterm is very much based on the big old duck problem. Sometimes it's clear that it looks like the big old duck problem. Sometimes it's the big old duck problem sort of turned on its side. Like, you have to understand the problem to recognize it in some other form. But for sure, for sure, people are right that the big old duck problem is a central problem that we need to know. And yes, usually appears on an exam in some kind of costume or another. So that's absolutely what we're going to do. Oh, wait, I'm just looking at direct chat. I understand there are acknowledgments in the direct chat about various homeworks that have or have not been turned in. I totally understand. I'm not going to deal with that like personally right now, but it's all good as long as the portal, as long as you still see the portal posted, then you are still welcome to submit homework into it, and you are still welcome to get all the points. And some of you owe me some, and I owe feedback to some. But the bottom line is this: now you're aware in Google Classroom that we are going to have an exam soon. I'm not the details of the exam, the logistical details are in Google Classroom, and the substantive details are made as clear as they can be possibly made in the practice document, the practice exam for that. We try to reduce a lot of anxiety and reduce a lot of surprises and reduce a lot of discussions by just giving you a practice exam like a week prior to the actual exam. So so we're gonna talk about this exam increasingly over the next few days. Right now, the logistical details are in Google Classroom. Right now, the practice exam that's posted is an old one, so it'll be revised and updated for like our purposes by this coming Thursday night. Again, all of this, but check out Google Classroom. There's just like details now in the material section. It's just an announcement. Just know, bottom line, the exam will be administered a week from this Thursday night. Posted a week from this Thursday night. It'll be due back right before class on the following Monday. Sorry. The actual exam will be posted not this Thursday night, a week from this Thursday. This Thursday, you'll get the final version of, or a version of your practice exam. The next Thursday, you get the actual exam posted. The actual thing is take home. You have the full weekend to do it, and it's due right before class on Monday, October 30th. Okay, again, we'll talk about it more, but you need to have those basic facts. And we will talk about the practice exam itself, and you may well have an opportunity in lab. You might, I will talk to your lab instructor. You might have a big opportunity in lab prior to your actual exam to like help each other and walk through the practice exam and see some solutions, stuff like that. Okay, but hopefully that. Yes, I want to get to the big old duck, which is definitely one of the problems on the exam. Okay, just raise your hand if you saw or if you can see that there is details about this in Google Classroom. Okay, great, good enough for me. Okay, so I'm not saying we'll never talk about it, but I want to do it in stages. So great. All right, thank you guys. Okay, all right. So yes, big old duck is the problem at hand. Oh, but one other preliminary here. I hope this doesn't throw off the person who, because you have this exam come now in the queue, a number of people have asked me, a number of people have asked me, is there somewhere where all the equations are sitting somewhere that we've had so far? Good question. Good question. Well, so the answer is right here. One answer is right here. Okay. Of course, I'm gonna. You may want to copy this down right now while I'm talking. I'm not gonna walk through all these right now, but this is like a little review sheet right now of the equations we've had so far. Of course, I'm gonna upload this PDF. So whatever. But the other thing is you'll notice and it's good to see them written you'll see them written in slightly different forms in different places. Don't be thrown by that. Like, you want to know the equations well enough to not be thrown if someone uses a Y instead of an X somewhere or something like that. But yes, these are the basic equations that we've had so far. You'll also find them on the inside cover of any practice exam we give you, like the old one that's already posted just as a sample. Some version of these equations are there on the inside cover. When I post or revise your practice exam, they will be inside there. And that also means that they'll be in your actual exam. The practice exam is meant to reduce surprises. The practice exam is meant as like a draft copy, actual exam. So you should trust it. You can't trust that everything will be exactly the same, but you should certainly trust the format, the structure, the types of problems, etc. So we don't give out a list of all the types of problems. We just give you the draft document. So you'll note that you're even given your equation on your actual exam. It's not a matter of trying to memorize them. It's really good that people ask me for them. You can see the material organized and see how the thoughts are evolving, but it's not about memorizing these equations. It's about getting to the point where you realize you don't even have to explicitly spend time memorizing them. They are to be understood and used and familiar enough that you're just familiar with them. But okay, so this is a sheet of the equations we've had so far as I'm concerned. Then on the next, I'm doing this fast because, of course, I'm going to upload this, but just so you know, on the next thing, I'm saying principles that we've established so far. Together, these equations and these principles constitute a list of what I would consider to be step 3 GDPs. Like, this is knowledge that you are allowed to and encouraged to invoke as like statements of general truth when you begin solving any problem on an exam. Like, some of them are in symbolic form, those are the equations, but those are mostly definitions, right? And then written symbolically. But then some are written in English, like these 3 different forms of Galileo's principle of relativity, which I'm not reiterating right now. I want to get to what that person asked about the big old duck. And even here, you'll notice, if you're careful, here, some of these are even abbreviated. Like, I wouldn't memorize this page. This is a reference guide to what I think we know. I think we know Galileo's principle of relativity expressed, first of all, as a statement like the laws of physics are the same at all constant velocities. But then from that, it follows that you can't do an experiment to establish how fast something is going in and of itself, right? And from that, it follows, like form number 3, that therefore there's no such thing as the velocity of something in and of itself. All velocities are relations between pairs of objects, right? So again, this is just like abbreviations here. You've got them in your notes, the real thing. But then it leads to form 4, which gets very mathematical and we're all still getting used to, and is like a big deal for homework 7. You'll see a lot of people are asking me for examples of how to use form 4. Totally understand that. You've only gotten 1 or 2 so far. It's still a little bit new to people. You're gonna, believe me, the rest of your physics study, in a way, I mean, physics 203 and 204 is studying different cases and examples of particularly how to make use of case 3 of form 4. But I do want you to have this knowledge organized in your mind in this way. Please know that all these forms are different ways of saying one principle. It is the principle of relativity. The more you can see how it's just different ways of saying the same thing, you'll see that you really get it. So case 3 of form 4 here at the bottom, we're going to be practicing more and more, especially in homework 7. But now, finally, I'm going to say right now, and I know again, we've always promised the pace of the course just sort of picks up as we go. Maybe the pace of my speaking does too. So now, to get to what at least one person asked and what I really want to get us to solving that big old duck problem in homework 6, which is where I'm going to turn my attention in a moment. The big piece of understanding that we want to have going into that problem is what I'm now going to declare to be the 5th form, excuse me, the 5th form of Galileo's principle of relativity. I haven't said it yet. I'm saying it right now for the first time. Again, I'm going to claim it's going to sound like something new. Oh, well, sorry. So the exact wording of it, I'm going to turn back now. The exact wording of it is here on the first page. I'm not saying that I don't think I've said this before. But if you really think, if you really understand that Galileo's principle of relativity says no matter what coordinate system you're in, no matter what reference frame, no matter what perspective for measurement that you're in, the laws of physics, whatever they are the same. They don't change from one perspective to another or from one coordinate system to another. Excuse me. If you really are starting to see that's what we believe in physics, and that all of our subsequent beliefs come from that, well, then if you think that the simplest possible version of a coordinate system that you know is a axis, right? Like everything we were doing in the first month of this course on problem number 1, number line, was all us looking at the world through the perspective, through the lens of a coordinate axis, the x-axis, the number line, right? That's a coordinate system. That's a perspective. Now it was just one dimensional. We were restricting our view of the world to what we could understand in one dimension of space. Well, if Galileo's principle is really true, that the laws don't change just because you look at the world in a different way, if the laws are the same in this coordinate perspective, this coordinate system versus this one, it also follows from that they're the same in the simplest possible coordinate system I know, axis. They're the same in the x-axis as they are in, say, the y-axis. In fact, if you really starting to see relativity, that all velocities are matters of perspective, then you really start to see that calling an axis x or calling an axis y is just a name that we're giving the axes. The name doesn't make any difference. Whether you're turning your head like this or turning your head like this, you might be viewing the world differently, but the world is still the world. So it follows that the laws of physics are, whether you're in the x-axis or the y-axis, whatever laws, whatever equations, whatever we figured out in the first month on the number line homework, we're now going to say it's also true if we turned the entire axis and made it vertical, okay? All the laws are the same. All the definitions, all the equations are the same, even in a vertical axis. And that means, here's where I'm going to read this now. That means we could say that for any axis we want, x, y, z. We can even say when we have a number of axes constituting one space at one time. That is what I'm going to say now. I'm just going to read this. Every n-dimensional physics experiment or physics problem, every n-dimensional problem, in fact, yes, every n-dimensional problem is equivalent to, can be regarded as n one-dimensional problems occurring simultaneously, like occurring at the same time, yet, and here's the key word to the whole thing, in red at the bottom, yet independently. Now, let me break that down for a second. This is the big old duck, the key to the big old duck. Again, I'm not trying to stall, I'm trying to set it up and why I saved it for this long. The key to the big old duck problem, which we're now going to solve together, whether you did or did not do it right yourself. The key to the big old duck problem, in fact, yeah, here, let me go, is the same as the key to lab 4. I believe it was lab 4, when you shot something off the desk and you had to, and it landed on the floor and you had to, it was a ballistic projectile and you had to like solve the crime of retrodicting where, how far where should the gun have been so that that bullet actually hits that spot, right? The thing about those two, about that lab and about the big old duck problem, let's start it. The big old duck problem appears to be a two-dimensional problem. I mean, it is a two-dimensional problem. It's a big leap. It's why, I don't, consciously or unconsciously, that may be why some of you were intimidated when you looked at it. It is intimidating. For the first time in this class, other than lab 4, we have things happening in a y-axis while they're also happening in an x-axis. That is definitely a step forward in physics. We're now entering the land of two dimensions. And as you see, that happens all over the place in homework 7. We're in the land of two dimensions now. And once we're in the land of two dimensions, once we're in more than one dimension, we might as well be in any number. That's why I'm using the number n over here. The thing is, once we're in two dimensions, the reason we have spent so long on all of these one-dimensional equations that we established on the first page here in the first month, the reason we've spent so long on these one-dimensional equations is that from here on in, the way to solve a two-dimensional problem is just to look at it as two totally separate one-dimensional problems that indeed are occurring at the same time. Like that's it's a two-dimensional problem because things are happening here while they're happening there. But the key physics insight, and it really is an insight, if you understand Galileo's principle, whatever form you like best at this point, you understand that what's happening in the Y direction doesn't affect what's happening in the X direction. That is the key. I'm going to start doing it. I promise. Those of you who are just like waiting for the equations, I promise. But the way to dive in is to realize that even something that looks two-dimensional or three-dimensional in physics, I mean, in lab 4 really kind of look three-dimensional in a way. Even if it looks three-dimensional, what you just stand back and you say, whatever's happening here, I use my equations. And whatever's happening here, I use the same equations. Like this is a world of physics. This is a world of physics. The equations are going to apply here. Maybe here there's going to be gravity, so I might plug in a gravity number here or something. Maybe here there's no gravity, so I don't plug in gravity. I'm not saying all the facts are the same, but I'm saying the laws, the equations, the GDPs are the same here as there. So what you do is you just approach each axis independent, and that's the key word. Independent problem. Whatever facts are happening here don't affect the other axes. You just solve each axis as you can in some kind of smart order. And then you realize that they're all put together at the end by the fact that they're all happening at the same time. The facts are independent, but the occurrence is simultaneous. That is GPR form number 5. I'm saying I'm going to use it now. You'll see I'm going to use it now to solve the big old duck problem, and really all the vector stuff that ends up happening in homework 7 is all an expansion of this idea, and the GPR form number 4, case number 3 that people need more practice on. It's all an expansion of this idea that each axis, that all the axes might occur at the same time, but they don't affect each other. So here we go. So let me just bear with me for a second. So I'm just going to draw this thing. So we're going to do the big old duck now, and we're going to use that idea to solve it. Sorry, just to pull it up really quickly. I mean, I know the problem, obviously, but I do not. Hold on. Sorry, bear with me for. Okay. Okay, yeah. So, and here you definitely have to do the 5-step method. I mean, this is, well, you get it right. And duck can't ever duck. Oh. Okay, right. Okay. Now here actually, I apologize. I'm going to make a correction. We could have done that, but okay. All right. So here, I'm pretending I'm you doing my homework, right? Or I'm pretending I'm you doing the exam. And again, let me emphasize, like, the whole reason any of these problems that you can practice and do the 5-step method, it's really meant for the exams. Like the 5-step method is really key. And again, I'll emphasize this more and more. Like if you noticed, I mean, the exam is take home, and it's open everything. So you got to understand that what your job is on the exam is to show me that you understand. So you really do want to drag the process out as much as possible. It really is about process. And the more colors you can use, the more different, like, here's my equations, but over here I'm writing in English, or here I'm putting arrows, drawing diagrams. Like, it's a presentation. It's like a poster, your exam. Like, honestly, I mean, or many posters. Your job is not to give me answers. It's to show me that you really understand where the answers came from. So anyway, so here I'm doing what you would be doing. I've produced my diagram. Now, granted, I'm looking. I mean, the problem gave me a diagram. Mine's very, very similar, but I've added some things that I really need. Oh, and there's even one more. Okay, it says south. yeah, the north and south thing is kind of itself is kind of confusing, but I've added some, like my diagram looks like the problem. It certainly, I think, includes all the facts of the problem, but I've included some more things to make it really useful in the problem solving. Like I've clearly labeled what I consider to be plus and minus. And notice now we're in 2 dimensions now for the first time. Sorry, I'm losing my screen. We're in 2 dimensions. So there's like 2 independent physics problems that are going to happen here. So I label plus and minus for one axis, and I independently label plus and minus for the other. And you saw, I even changed my mind, but like I could make down positive if I want. And in some cases, it's very useful to do that. And it doesn't matter. I can make that decision regardless of what I did in terms of left and right on the horizontal axis. They are 2 different problems. Okay. So, but I've labeled positive, negative. So I've therefore labeled my values with positives or negatives. Also notice one little addition I've made here in my diagram. I think I've done it consistently. I'm now really trying to distinguish like the X world, the horizontal world, from the Y world. So I'm adding subscripts. Now, this can get a little confusing to people. I just have to warn you. I'm adding subscripts to make, like you see, like V naught X is plus 20 meters per second. That's from the problem that was given, but V naught Y is plus 30. There's 2 different numbers, 2 different pieces of information. One is how fast the duck is going horizontally the moment I start my stopwatch, and the other is how fast the shot or the ammunition, the shot is going out of the shooter's hand the moment I start my stopwatch. Now T equals 0 is the same for everything. But this is one problem. So so the X world and the Y world are occurring simultaneously. So I do have one stopwatch on this whole thing. So whatever I mean by naught is the same. But there's the vertical initial velocity and the horizontal initial velocity are 2 different things. So I'm putting subscripts. On stuff to mark whether it's horizontal information or vertical information. Now, sidebar, so you see I'm starting to use 2 subscripts on my velocities, which was a big sort of training aspect of teaching you GPR form number 4. Like there we start getting used to the double subscript thing. I do have to sort of caution you that these 2 subscripts are not doing exactly the same. I don't want to get all into this, but these subscripts are about denoting whether it's from the perspective of Y or the perspective of X. I mean, I guess they are really doing the same in a way. I mean, I'll just leave it at that. But notice we're starting to be very careful about our velocities. One of these is measured from the perspective of the x-axis, and the other is from the perspective of the y-axis. Okay, and I'm adding that to the problem. And the acceleration, you could put a 0 there too if you want to make it consistent. But we do know that like the acceleration is going to be constant throughout the problem. So all right, anyway, so that's my fact pattern. Okay. And if this were an exam, I would probably recommend saying something like, okay, there's my step 1 DFP. I think it's good to keep track of it. Okay, so that's my setup. I'll get to it. All right. So the question of this whole thing is really very much like lab 4. It's how far north should the big old duck be at t equals 0, right? That is the question. At t equals 0, what is x? And okay. In fact, well, yeah. We can even call sorry. So we can call this the x-axis if we want, and say this is x equals 0. So we're looking for how far to the left would the duck be? We're looking for how far to the left, to the north, must the duck have been at t equals 0 so that the bullet and the duck meet and the duck gets shot, right? The duck is going to meet the bullet somewhere along that y-axis, somewhere directly above the guy that shot the bullet. But the question is, how far back should the duck have been in order for that to happen, right? This is much like Lab 4, where you're in effect solving a crime. You're not predicting the future, you're retrodicting the past, but it comes to the same idea, right? You're assuming that the laws of physics connect all these snapshots of time together into a movie. So, okay, so our question is, where should the duck have been so that it gets hit by the bullet? So really, before I start applying all the equations or setting up the equations, let's note in English, what we're really asking here is, can we come up with equations or ways of thinking to ensure that the duck and the shot arrive at or occupy the same point in space at the same point in time, right? That's what this question's really asking, at the same point in space at the same point in time. We want a collision, right? If we want the duck to get shot. So, okay, so we want them to be, both those objects to be at the same point in space at the same point in time. That's our goal. So okay, so what's the question, right? So that was step 2. What is the question? Okay, so what am I going to do? Step 3, GDP. I am first and foremost going to invoke, and you should really write this. All right. You should write this if this were the exam and you hadn't said anything about this yet in the exam, you would write this fully out, like Galileo's principle of relativity, form number 5. Now tell me what you mean by that. But what I'm saying here in this case is the thing I've said twice already this class. All 2D problems. Every 2D problem is really, or is in effect, 2 1D problems occurring simultaneously, yet independently. So that means I can separate it and start applying the physics to the axes. So what I'm saying here in blue, I'm saying the first question I want to ask myself then, if I'm allowed to break up this physics problem into smaller individual separated physics problems, really the first, and you could even call this a sub question if you want, or something like this is like a sub goal or a sub question. I'm asking myself, can I use physics to solve for how to predict how much time it would take this shot to arrive at the height it needs to arrive at in order to hit the duck? Let me be clear about that for a second. Like, so again, many of you actually like did this first step, knew to do this first step first, and knew to do it correctly. And again, just to be honest, like over 30 years of doing this, when I just do this in class live in front of people, like generally that's a big leap for a lot of people. And I'm very like a lot of people don't think necessarily to do that first. I'm pleasantly surprised that a lot, I really am impressed that a lot of people got this part right at home. And maybe it's because we have more resources that are, I don't mean to insult anybody. I think it's great. Either people are getting smarter over the years, or like you're a very, very smart group, and or you're using resources like very, very well and studying well, and like looking back, no matter what it is, a lot more of you did figure out this first step than I'm sort of used to in the past. So that's terrific. Let me explicate it though. This first step that we're doing, again, because not everybody did. The first step that we're doing is figuring out how much time it would take this bullet to go from the ground up to the original given height, the height that the duck is at of whatever it is, 30 meters or so. Sorry. I think it's, we'll look up in a second. I think it's 30 meters. Maybe it's whatever. By doing that, if that's what we're going to solve, if we're going to now apply physics to the y-axis by itself, what we're really implying in our minds or believing in our minds is the only thing we care about the duck at this moment is we care how high the duck like always is in the problem. The duck is like always at this height. That we are noting. Other than that, we don't care that there's a duck there at all for this stage of the problem. We're saying physics will demand that a bullet takes a certain amount of time to get to a certain height, whether there's a bullet, whether there's a duck there or not. We are breaking apart the problems into separate one-dimensional problems. Okay, so and if we weren't allowed to do that, we couldn't do this. So solve for time of bullet to reach height. Now I'm just going to look back at it. I think it was 30 and 40. Yeah. Oh, it's sorry. It's for, yeah. To reach height of y equals 40 meters if thrust up at v naught y equals 30 meters per second, right? These are all positive. And assuming that we're all near the surface of the earth. Oh yeah, and it says, I should have put it in my diagram. I'm sorry, one thing I didn't put in my diagram, it does say in the fact problem, we're all assuming that this is all on Earth, near the surface of the Earth. So we're also assuming that AY is a constant and it equals the acceleration due to gravity, right? We're assuming that the constant acceleration, which we're calling approximately 10 meters per second squared, although it's going down, right? Okay, so side note here. I mean, I've labeled my coordinate system so that up is called positive and down is called negative. So therefore, the downward acceleration of gravity is a negative number. It isn't always, but it is here if down is called negative. Just fixing that. So that's all part of the given fact part. And again, on the exam, G is G. If you're near the surface of the Earth, G is G. And if problems involve numbers, unless you're told otherwise, you can approximate that the magnitude of G is 10. But it usually will tell you. Okay. So assuming AY equals a constant, which equals G. And all this, so we're assuming that, and note, this physics that we're about to do, this y-axis physics, let's say, this y-axis physics is unaffected by anything the duck does. Okay, so what it is just going to be the physics that we were practicing like last class. We know the displacement, this is one axis physics. It's like, it's free fall, it's up and down motion, constant acceleration, like we were doing last class. So we know the displacement, we know the acceleration, we know the initial velocity. What we only don't know is the time. So time is involved and acceleration is involved. So certainly a equation that I highly recommend, and I'm still in GDP land here. I think we're talking this. Sorry, be more specific. We're all in the y-axis. So you notice what I'm doing. Please note what I'm doing. I'm taking an equation that we already have, one of the one-dimensional equations we already have, and I'm just applying it to the one dimension known as the y-axis. So I'm putting y subscripts on everything to make that clear to myself. I do think it's fair to say that the initial height, the ground, is the lowest point in the problem, where the bullet starts when the gun goes off, is zero. Like, I'm deciding that. There's no reason not to. So this is the equation I'm doing. So now I'm in step 4 for this part, at least. Okay, so I'm just working it out. So I say y equals, well, I'm going to plug in. So y we know is 40 meters. Okay, now I'm going to be careful about signs here, and you may want to make a note of this. I'm going to be careful about signs. I'm saying anything that's up is positive, anything that's down is negative. I'm not looking at left to right. I'm just looking at up and down. Up we called positive, down we called negative. This bullet has to go up 40 meters. So it's literally positive 40 meters equals 1/2. Okay, what's the acceleration? The acceleration is gravity, is 10, but it's downwards. The acceleration, like gravity always pulls everything down. So gravity is -10, right? Times, so it's negative. Gravity is negative. That's important. Time is what I don't know. That's what I'm solving for. So it's t squared plus initial velocity. Here, let me write it clearly on the next line. The initial velocity is not zero. It's not zero, right? And this goes, people were asking questions about this last week. Good questions. Like, we're throwing something up from the moment, like when it was sitting in our hand, it might have been zero. That's a while back. That was a different physics experiment. Now I've started my stopwatch from the moment this thing got released from my hand. I shoved my hand up, and by the time the thing came out of my hand, it was going already at an upward velocity of 30 meters per second. If it weren't, it wouldn't go up at all. So it does have an initial velocity. We don't cross out that other term. It's 30, it's positive 30. And t is that same t that we still don't know, that we're solving for. Okay. I know everything else. I don't know t. The t here that's unknown is the t that I need. I won't be done with the whole problem when I get it, but it is the t that I need to figure out how much time the bullet will take to get to the height of the duck. All right, so I'm going to simplify. So I've got an equation here. It's a quadratic equation. I've got to be careful with it. So what am I going to do? I'm going to just sort of clean it up a little bit. I'm going to say, fine, negative. I'm going to subtract the 40 from both sides. I'm going to make this look like a standard quadratic equation from like a math class. So I got negative t, 5t, plus 30t, minus 40, all equals 0, right? And then I'm going to divide both sides by -5 just to make this look as easy to deal with as I can, or as familiar to deal with. You could do other things. You could even plug this into a calculator if you like, but I'm going to say it's t squared minus 6t plus 8 equals 0. I hope you see how I did that. There's other things you could do. I'm just looking. Oh, wait. Oh, I'm looking at, sorry, I missed the chat. How long ago was this? 3 minutes ago. Okay, so sure. Good question, Maria. Yes. instead of using X and Y subscript, I'm pausing. It's a really good question. Yes, especially if we're talking about on the exam. So she's asking, well, you can see, instead of using the X and Y subscripts, can we use different colors? Absolutely, yes. So two things. First of all, I am a big fan of different colors on an exam. Of course, whatever you do, just like make it, make a legend or a key or whatever at the beginning. Say I'm, using red for horizontal. Use it, but yes, you can. I will say we want to get in the habit of subscripts for other contexts, like when we're really doing like the relative velocity stuff, like in homework 7. Then I think it's almost unavoidable to use the double subscript. So it's a good habit, but especially if here you think this is a different context and it's too confusing to use the double subscripts here when you know you're going to use them for that GPR stuff, that by all means, I'm totally yes. So yes, good question. And keep these questions coming because we definitely all do want to know this problem inside and out. And again, usually it appears, but in some, okay, great. Awesome. Thank you. All right. So I'll go on. All right. So I have this now, T squared. Now, this is a quadratic. There's just no way around it. There's different ways to solve this. The way we tried to design the numbers so it's not crazy. Like you could use a quadratic. You absolutely could use a quadratic formula here. I bet you, if you're like me, I never knew that thing was actually ever going to be useful anywhere other than on like the quadratic formula quiz in the math class. But no, it really does mean something. You could use a quadratic formula, or you could complete the square. But I think in this case, we gave you something we tried to make something that's factorable. So you could also use a graphing calculator, etc. Or even a solving calculator. But what I do is we have this. I think it's factorable. In other words, I think it's factorable. Yeah, it's factorable. Right? Some of you are more, whatever. I think you can do that. Like, because the -4 times the -2 gives you +8, but -4 plus -2, the -4t plus, like if you FOIL that out, you'll see it. I mean, FOIL. So now wait, so what does this mean though? So I'm not done, right? I think I'm done in a way with the hardest part of the problem, but I'm not done. What this means thus far. Keep forgetting. Oh, there's something else in the chat. Sorry. Okay. Sorry, there's two. Okay. First of all, okay, so we're not done. We're right now just solving for how much time does it take the bullet to get to this height, given an initial velocity of 40 meters per second and a downward acceleration of -10 meters per second squared, right? Given those two things, the math has spat back two possible roots to this quadratic. Now, we all know math, we think we know that mathematically that makes sense. A quadratic is if you graph it's a parabola, it crosses the x-axis at 2 points. Like we know math-wise, quadratic equations give us two answers. But math is supposed to be describing the physics. What we don't want to do is just like pick one of those answers. No, if the math provided them both and provided them with equal weight, they both signify something in the physics. Now we have to be careful here too, depending on how the physics question is asked. It's not always the case that we're always interested in both of the answers or all of the answers that the math gives. Depending on what we're asking, we might be more interested in one answer than another. But I don't think that's the case here. What we're asking here is just when will the object be at that height? And given the facts that we told the math, there are two different times that the shot will be at that height. And to cut to the chase, since a lot of you did write this in the homework, and I'm pleased, the reason that it even asks, yeah, okay. I mean, it even asks in part B, how could this be? The answer is because if the shot is fired up with positive upward vertical velocity, but yet gravity is pulling it down, that means this shot, independent of the duck, this shot is destined to go up, reach a peak height where it runs out of all of its positive velocity. Let me be more clear. It's destined to lose velocity, lose positive velocity, until it has zero velocity. And then if acceleration is truly a constant, if acceleration is always negative, even when this thing reaches a velocity of zero, it's going to keep losing velocity. Well, how do you lose velocity if you have zero velocity? You go into the negatives. That means you come down, right? So it's velocity numbers, like in terms of like the charts and stuff that we were starting to think about last time. The velocity numbers would be like positive 30, positive 20, positive 10, 0, then negative 10, negative 20, negative 30. The velocity is always going down. The velocity is always going down. That's why the acceleration is always negative. Note, the acceleration is a constant. Whether you're moving up or moving down, the acceleration rule, the gravity rule says you're always losing 10. So on the way up, you're losing speed. On the way down, you're gaining speed, but you're always losing velocity. Please note that if what I just said confused you at all, that does not mean you're dumb or you shouldn't be in physics, but it means you want to think about it more before the exam. I'm going to say it one more time. In fact, we often ask this in the exam. If the acceleration is constantly negative 10, that means we're always losing velocity, whether we're going up or going down. But we are losing speed on the way up and then gaining speed on the way down. This is the difference between a vector quantity and a scalar quantity. And so just think about that, or make a note of it, or make a note that you have to ask me about it if it's not clear. But what does it do for me here? It means the shot is going to go up and then it's going to come down. So as far as the math and the physics are concerned, there are two times that this thing is destined to arrive at that height. Nobody in the physics ever specified that you had to hit. It's not a trick. It's like an important insight. No one ever said you've got to hit the duck when your bullet's on the way up. It's just, we just want to hit the duck, which is mean, but right. So we're not distinguishing between these two times. So hold on. And again, we're not done with the physics problem. We're done with the sub question, but also note this, it really makes sense. This whole thing that this is all the facts that are independent of the duck. They're just dependent on the duck height. Notice it really does make sense. And you might even put this in your exam if you were. sidebar. If we're really looking at this, it's not a side. I mean, whatever. No comment. If we're like doing the physics of this shot, independent of the duck, then this really is just like a physics exercise practice that we were doing last Wednesday. I could just ask myself, how much time would it take this shot to reach its peak height? Like if it doesn't intersect with the duck, or if we do it fast enough, the duck hasn't gotten there yet. Like how much time would it take for this thing to reach its peak height? Its peak height, its natural peak height. Like it's, I don't know what, or I could even ask, what would that peak height be? But assuming that it has a natural physics motion, according to physics laws, independent of the duck, I could ask how much time would it take to reach a peak height? And to cut straight to the chase, you could back up and look at this more slowly with like many equations if you want for practice. But look, I know that A equals like A sub Y equals V sub Y minus V. I know that, and you could flip back to your equation sheet. I know the definition of average acceleration is change in velocity per time. So I could rewrite that. This is what we were doing last Wednesday. I could just say, look, I want to know how long this thing would take to run out of speed entirely. I want to know how long it would take to get to instantaneous velocity of 0, right? So in effect, I'm asking how long would it take to decelerate down from 30 meters per second down to 0 if it's losing 10 every second, right? And you can do it strictly with the equations if you want, or you can intuitively see. If it starts at 30 meters per second and it's losing 10 every second, I hope you can intuitively see, even if you wouldn't have thought to think of this, every second it's losing 10, it starts with 30, it's going to take 3 seconds to run out of speed, right? Its natural peak height would occur at 3 seconds. And doesn't that make sense? It's right in the middle. It's equidistant between 2 and 4. Doesn't that make sense? In other words, if it's on its way up, when it hits the duck, it's got 1 more second to keep going, or it would have had 1 more second to keep going. But if it does keep going, goes up to peak height, then there's going to be 1 more second from the peak height to hit the duck on the way back down. The 2 collision points are symmetric with respect to the peak. Like I think and if you solve for what that peak is, if you really get, like we literally did on Wednesday, you could do it in your head on average. I'm just going to say this for those of you who are like in it to win it. I mean, you're all in it to win it, but like it starts at 30, it's running out of steam to 0. So on average, it's going up at a rate of 15, right? On average, on its way up, its average vertical velocity is 15. It's doing that for 3 seconds, 15 meters per second on average for 3 seconds. So it would travel 45 meters if left up to its own devices. I'm just verifying like its peak height would have been higher than the duck. The duck is at 40. It would have gone 45. We can do that in our heads once we get used to this. So for sure, it could hit the duck on the way up or the way down. The duck is in its way. All right, anyway. So my point is we're going to get 2 possible answers. The duck should either be at some location like close by so that as soon as 2 seconds elapse, they both hit. Or the duck should be way far back, so it's got a lot more time. So it's got 4 seconds to travel so that give the shot time to go up and then come down and then hit it. Like there's going to be 2 possible answers to this whole equation. I'm looking. Sorry. Cool. Sorry, I'm seeing things in the chat. I'm glad people are. It was like a long time ago. I'm sorry. Wait. Oh, great. Okay, so one person is telling me that they understand this a lot better. That's great. I totally. Person who's telling me they understand it better now, definitely like screenshot that and submit for points. That helps me a lot. But then someone else is also asking. Yeah, I'll just repeat one more time and then you can play. Like I'm saying, this thing is going to go up and then come down so I'm just repeating something that I said because someone's like intelligently asking in the chat. The accelerate. Oh, cool. Okay. Oh, and yes, this is very related to lab 4. Yes, good. And I'm watching the time as well. Okay. It's important to see gravity, that the constant acceleration due to gravity, due to free fall, the number that we sometimes think about is 9.8. We sometimes round to 10. One big question a lot of people ought, so I'm backing up for a second. A lot of people get confused going into the exam. Like, do we make gravity a negative number? Like, and a lot of people want to, are we supposed to memorize that gravity is negative 10? Or sometimes I'll say in class, gravity is 10, or the acceleration due to gravity is 10. And then people will like chat me and say, wait, I thought it was negative 10. Like, wait, did you just make a mistake? We got to be clear what gravity is, what the number is it points down. That we know. The acceleration due to gravity always points down. Whether you make that number positive or negative, that depends on how you've labeled your coordinate system. That depends on what perspective you're in. This is the Galileo point, okay? So first, I just want to say, I don't want anybody to memorize that gravity is always negative. That is a choice. And for example, in a problem where something's always falling down, like the bolt problem where nothing ever goes up, it's not worth it to make gravity a negative number. You're going to make your calculations much harder. So gravity is whatever it is, but it's constant. Whatever sign it has, here's my big point. I'm sort of backing up. Whatever sign you make gravity, you make it that sign for the whole problem. You don't change it midway in the problem. A lot of people do that on exams. You don't say that gravity is negative while you're on your way up, and then it's positive on your way down or something else like that. So for example, in this problem, the gravity number is always negative. We're saying in this, because down is negative in this problem. So gravity, the acceleration is always negative, whether we're traveling up or we're traveling down. And therefore, the thing the person wants me to repeat is, if gravity is negative, whether we're moving up, whether we're velocitizing up or we're velocitizing down, gravity is negative either way. That means no matter what we're doing, we're losing velocity. Our velocities are getting smaller every second. If acceleration is negative, that means velocity is lowering. Like, that is a truism. If acceleration is negative, that means you're losing velocity. Now, what I'm saying to everybody, and at least one person is asking for re-emphasis, and I don't think that he or she is alone, I'm saying, okay, the velocity numbers are going down the entire time something goes up and then goes down. The velocity numbers are getting lower for the entire round trip, even though the speed numbers are doing something different. i.e., I'm saying the velocity numbers for this shot, in this example, are going like positive 30, positive 20, positive 10, 0, then negative 10, negative 20, negative 30. If you wrote those in a chart, or you just wrote them out on a piece of paper, you would notice the velocity numbers are always going down. First, they're going decreasingly positive, and then they're getting like increasingly negative. Like 30, 20, 10, 0, negative 10. You're always going to the left on the number line, so to speak. But the speed numbers are not. You're going slower, then you're going faster. This is the difference between speed and velocity. You're going slower on the way up and then faster on the way down, because on the way up, your velocity numbers are positive and they're getting less and less so. But on the way down, your velocity numbers are negative and they're getting more and more so. This is what I'll say one last. The reason things slow down on the way up and they speed up on the way down is because gravity is always pulling them down. So, okay, for what it's worth, that's okay. That someone asked me to repeat. If that still didn't work, definitely let me know or watch the video again, et cetera, et cetera. But it's a good question. Okay, so now we're almost done with this problem. We've done the hardest part. The two hardest part. Well, we've done a lot of the hardest parts. We've first separated out. We've like got undistracted by the duck. We're saying to ourselves, I know it's a two-dimensional problem, but I don't care. I'm going to just look at one dimension at a time. Major physics secret there. Then are saying, if we're just looking at this dimension, the vertical dimension, we're setting up the equation and we're noticing, oh my God, we have to solve for a quadratic. We've never done that before, but you do know how to solve for but it's math. So we do the math. We solve the quadratic by whatever means. Then we find out the quadratic gave us two answers. We have to have the physics conceptual understanding to see why they both make sense and take them both seriously. So that's what I've just done. Now I can do, I think, the more grindy part. I can now say sub-question 2, in effect, if you like. Sub-question 2. In this time, in these time intervals, how far would the duck travel, given all the information we know about the duck? So now we're shifting our attention to the duck. How far would the duck travel horizontally? So we're now, and this is going to be some plugging and chugging once I get this set up. Yeah, okay. Note, we've now switched to the independent x-axis. We're now just going to do a bunch of physics on the duck in the x-axis, and but the fact that we've borrowed from the y-axis, the only thing that we're taking into account from the y-axis is the time that we just solved for, because the only thing that the two axes have in common is that they're happening at the same time. That's the key to this whole thing. They share a time frame, but everything else is independent. So we went to the y-axis first to solve for that time so that we can use that time. So the only link between the two is time, and everything else about them is independent. And quick warning, if you're still with me in terms of the exam or something, sometimes we do a problem just like this on the exam, but we literally invert it or something. Like we change the fact so that something's going along on the y-axis and like you shoot or something, or we just give you different information. In other words, what you might have to think about on the exam is, which axis should I solve for first in order to get the time? That might be where the thinking comes in, especially if you're hearing me right now, make a note of that. Like there's no script as to which axis would, but if you look at the facts of both, you can tell, like, the physics was predetermined on the y-axis. Something would take a certain amount of time to get to a certain height due to gravity. But so we did that first. But that, anyway, that was a choice. That's where practicing exams comes into play. Notice that I chose to do the y-axis first. But if you were taking the exam and you chose the x-axis first and you hit a wall because you just didn't have any information, like you were solving for the time, but you didn't have enough other information, that doesn't mean that you're all messed up or you should quit physics or quit life. It just means, oh, okay, maybe that was a bad choice. Maybe I should try the other axis first. Like, and that's fine. Okay, so we're going to go to the x-axis now. X-axis, this is just like the lab now, just like the lab. I could even say we're in the so we're in the x-axis now, right? I'm going to write down any equations, or I'm sort of back to GDPs. I'm going to write like any equation or knowledge or truth that I think will be helpful for the x-axis, right? And maybe because the YT squared thing, the AT squared thing seemed so helpful before, and I feel like it's working for me. Maybe I even write the same equation again. Some of you did, some of you didn't. Maybe I write that same equation, but now applying to the x. But even if I write that equation, I'm going to notice, or I hope I notice, that just like the lab, the acceleration in the x-axis is 0. Right? There's no gravity in the x-axis. This is what we mean by them being independent. There's no gravity in the x-axis, so things don't have any reason to accelerate. They maintain constant velocity. So that whole term dies. So what we're really saying is, we're saying what some of you might have just realized anyway. We don't really need that whole big equation. And also wherever the thing starts is what we're solving. In fact, call that 0 if you want. So we're really saying this, which is really the same thing as saying this and rearranging it. This is like displacement equals average velocity times time. And the average is the same as it is at any moment, same as it was at the beginning, all in the x-axis, because there's no acceleration in the x-axis. However you want to put it, it's all the same thing. And I know someone's here. Okay, and I know we have 5 minutes. So now we just have to solve. Oh wait, I'm sorry. I'm saying all this. This is all true for the first half second, and then there is acceleration. Sorry, because a for the first half second for t equals 0.5. So first, in that first half second, right? For the first half second, there's no acceleration yet. It's just going along at whatever that given 20 meters per second. I'm doing this fast now because I want to finish this before we have 4 minutes. I'll just finish it. We know that this thing first, this duck first travels for 10 meters before it even hears the shot. Before it reacts to the shot and starts accelerating. Like for some reason, the duck is going along. It hears the shot and it's like, oh, and it freaks out and then stupidly starts going fast. Well, maybe not stupidly, starts going faster after it reacts to the shot. So it does 10 meters no matter what first. Then it accelerates. Then AX equals 16 meters per second squared. So now the duck goes, I'm going to do this fast. It goes for either 1.5 seconds, right? Where did I get 1.5? 1.5 equals 2 minus 0.5, right? The total is going to be 2 seconds, or the total is going to be 4 seconds, we said. So the two possibilities we have to solve for are, do you see what since the bell's about to ring, we're going to plug in these two different time possibilities and get these two different answers and add each one of them to 10, and that will be our final answer. So you have 3 minutes. Okay. Right, so 2.25 times 8. So this one is up and this one is down, right? So 18.8. Does that make sense? Sorry. 18. No, sorry. Oh, yeah. Sorry. 18 plus 30. So X up equals 30 meters and X down equals, I'm just recopying it. And you do have to have that initial velocity of 20 because that's what it's doing the moment it accelerates, right? So this is right. And we're just about done, but we will be done. 3.5 times 8. So 98 plus. So X up equals 30 meters plus 10, and X down equals 168 meters plus 10. Why 10? Because that's the bit that the duck does no matter what before it even accelerates. So the two possible answers are that the duck has to be placed at 40 meters before 0 if we want to hit it on the way up, or 100, and I believe, did I just hear a voice? Or a negative, or 178 meters to the left of the 0 if we want it to be shot. One is for up, the other is down. And again, and it's sort of a stupid detail in the problem, but it is a detail in the problem. And I think we just and last thing, I mean, it's 1:30. You've been very patient. I think we're done with this. I hope this was helpful. Both routes are physically, answer part C. If it had accelerated the same constant rate but towards the north, and we can talk about this more Wednesday if you want, that would be interesting. The acceleration would then, the duck would then turn around. But there would still only be two answers to the problem. We can discuss that Wednesday, but there's no matter what, there's two answers to this problem. There's only two possible places to put the duck to have it be hit. If you want to press me on that Wednesday, you're happy to. Sure. Yes, you definitely, wait, I'm just seeing in the chat. Oh, very different from what you thought, but it makes good. You definitely need to do the 5-step method for the exam. That is really the purpose of the 5-step method. Just absolutely on the exam. The more you drag it, yes. I mean, I'll repeat that a number of times, but yes. Bye. Yes, thank you. Great. Okay. Have a great day, everybody. Good listening. Good time. Bye. Thank you. Okay. Thank you. Awesome. Yes. Have a great day. Okay, I'm going to turn off the recording.